Okay, boys and girls, hello. This is going to be your video review for the second part of the first trimester in which we are studying physical geography. Now, before we start, there are two things that you need to know. First of all, do not just watch this video. Pause it in this moment, go find your notebook, sit down in a chair and study this video. Take notes of this video. Write as a title, Physical Geography Review, and take notes of this video. It is not just watching the video, you have to study it. Second point, I am going to let you know which parts are going to count for extra points and which parts you need to know. You really need to answer, because those parts are going to be your grade. All the other elements are going to count for extra points. So I would advise you to study absolutely everything, because with the extra points you can help your average, you can help your grade. But if you only want to focus in certain things, then it is okay if you just answer what you need to know. So I will let you know when we're talking about one thing or the other. First, we're going to start with some properties here, some geometrical properties about the ellipse. And it may seem like a bit weird to study geometry here in geometrical shapes such as the ellipse, but these are going to be very important, as you already know, when we study the orbit of the Earth. So this is the ellipse, and basically over here I have shown you the most important parts that we have. For example, the ellipse is drawn in two axes. The axis that is going to have the longest section of the ellipse is going to be called the major axis, and the axis that is going to have, let's say, the smallest part of the ellipse or the lowest part of the ellipse is going to be called the minor axis. Two things that are very important for us are going to be these two circles over here that are the vortex, vortex 1 and vortex 2, and of course over here the foci. I have already tried to explain you what is the foci and what it is, why it is so important for the ellipse. However, I found a video for you in YouTube, and I am sure that if you go and watch it, you will understand a lot better. And finally, well, how long or how short the ellipse is, that is going to be called the eccentricity, and that is also very relevant for what we are going to be studying here. So again, if you pay attention here, you have the two axes, the y and x axis, the major and minor axis. Then you have the two vortexes over here, the foci, that is the plural of focus, and the eccentricity, that is how long or how circular my ellipse actually is. Well, if we take this, well, please, by all means, stop this video right now and go watch this video about the two foci. In this video, these two poles, these two pins are going to be the foci, and we have this red string attached to the two foci, and this other, let's say, piece of wood or this pencil is going to be drawing the ellipse precisely by, let's say, the limitations that these foci are setting into my two pins. So you will find this link in the description. Please pause this video and go watch this other video about the ellipse, okay? So just so that you understand better what are the foci. So why are we studying the ellipse? Well, because in the 17th century, Johannes Kepler discovered that the planets were actually orbiting the sun in elliptic orbits, not in circular orbits, but in elliptical orbits. So all these, let's say, geometrical parts of the ellipse that we have seen are going to have a very important part in the movement of our planet. First of all, we need to know something really important. Usually we think that the sun is in the center of the Earth's orbit, but it is actually not. It is actually in one of the focus of the ellipse, of the orbit. And I would advise you to think as much as you can. If you think that the video that you saw about the string is related to this, if the sun, with all its gravity, is pulling the Earth like the straw is limiting the movement of the pencil, right? Perhaps there is a relation there. I would invite you to think about it. Then we are going to have two very important points in the position of the Earth that are going to be the vortexes. When the Earth is in the vortex closest to the sun, to the focus of the sun, Then that is going to be called perihelion, which is the point in which we are the closest to the sun. And when the Earth reaches the opposite vortex, that is when the Earth is the farthest from the sun, that is going to be called the aphelion. So just remember that peri means in the surroundings and helion means the sun. And aphelion, you usually see an A in the beginning of a word when it means without. In this case, I made deeper research, and apparently this doesn't come from a without helion, the sun, but from apos helion. That is why we have the P here. And that means apos in Greek means far away, so far from the sun. This is going to be the position in which we are the farthest from the sun. Now, the eccentricity. We have seen basically all the geometrical parts of the ellipse, how they are related to Earth's orbit, but now we're going to see the last one, which is the eccentricity. As we said, the eccentricity is how long or how circular my ellipse actually is. And the thing with Earth's orbit is that it is very close to a circle. The eccentricity isn't really big. However, if we pay attention to the size of this orbit, we are talking about 5 million kilometers farther from the sun in the aphelion than we are from the perihelion. In the perihelion, we are 147 million kilometers away from the sun, and in the aphelion, we are in 152 million kilometers away from the sun. So they are more or less 5 million kilometers of distance when we are in the aphelion and in the perihelion. So now, these movements of the Earth is moving around the sun in this orbit that is an ellipse, and that movement is called revolution, right? And it is moving counterclockwise. That means that it goes against the clock. And well, this process, this revolution movement, lasts 365 days with a quarter over there, right? That is why we have these years in which we have one more day. Then we have the rotation, the movement of the Earth called rotation, which is the movement in which the Earth is spinning around its own axis. And this process, of course, takes 24 hours, right? That is our day. The division between the day and the night lasts 24 hours, right? The thing that is really interesting here is that the axis of the Earth is not in a straight angle. It has this tilt, this inclination of 23 degrees. And that is going to be really important for our planet. Why? Because that is going to cause the sun rays to hit differently depending on the time of the year. So when the Earth is in the perihelion, which is actually when we are the closest to the sun, if you see here, the ray of the sun is hitting the southern hemisphere. You can see it right here. It is not quite hitting the northern hemisphere. So this is when we in the northern hemisphere are going to be in winter, even if we are the closest to the sun, because the sun rays are going to be hitting the northern hemisphere, as you can see here, when we are in the aphelion. So that is when we are the farthest from the sun. We are going to be living summer in the northern hemisphere. So this is going to cause that we actually have different seasons depending on the on the hemisphere in which we are standing. We basically have the opposite seasons when we are in the northern hemisphere than when we are in the southern hemisphere. So which are those seasons? Well, we have 4 seasons, and if the month lasts 12 months, then each season is going to last basically 3 months, right? And as we are moving counterclockwise, we first have the winter, then we have the spring, then we have the summer, and finally we have the autumn. But this only happens in the northern hemisphere, because in the southern hemisphere we actually have the opposite seasons, because precisely of the tilt in the axis of the Earth. So when we are in winter, they are going to be in summer, because they are going to be receiving all the sun rays. And when we are the other way around in summer, they are going to be in winter. So all you have to do is always pay attention to the opposite side of the cross over here. If we are in winter, then they are in summer. If we are in spring, then they are in autumn, and the other way around. Precisely, again, because of the tilt in the axis of the Earth. We are going to be receiving the most amount of sunlight depending on the position in the orbit of the Earth. So, in which days do we change these seasons? Well, if we start here in winter, we're going to have our first change of season the 21st of March, and that is going to be an equinox. Then we move on to the summer, and the solstice of summer is going to be in the 21st of June. The equinox of autumn is going to be the 21st of September, so we have just passed through this equinox. And finally, the solstice of winter, in which we are going to be moving towards winter, is going to be the 21st of December. These dates change within the years. Sometimes it is the 20th, sometimes it is the 19th, but we can basically round it up to the 21st every month, right? Every 3 months, actually. So, again, there are some patterns here. If you see this line, we're going to have equinoxes along this line. These two opposite sides of the line are going to be equinoxes. And this other line, in the two opposite sides, we're going to have solstices. So it is really easy to know which is a solstice and which is an equinox if we just pay attention to the name. Again, remember, equi means equal and nox means night, right? So these are going to be the periods in which day and night are going to be more or less the same length. So you are looking for seasons in which you don't have big changes, right? You have a nice climate which isn't changing a lot. And those very nice seasons are going to be basically spring and autumn. In spring and autumn, we are going to have the same ratio of day and of night. So it is not going to be really hot, it is not going to be really cold, it is going to be in the middle. But what happens when we have a solstice? Well, when we have a solstice means that the sun is static. And that is because it is going to be either in its maximum duration, and that is going to be in the summer, or it is going to be in its lowest duration, and that is going to be in the winter. So in the summer, we're going to have longer days than we have nights, and in winter, we're going to have longer nights than we have days. So these two seasons have very extreme changes, right? You're either going to have a lot of light, or you're not going to have enough light at all. And in these two other seasons, which are the spring and the autumn, you have very mild changes. Things are not changing that heavily. As opposed to it, in summer and winter, we have very strong changes. So you just need to remember that, because just remember, when you enter autumn and when you enter spring, you're going to have equinoxes. The day and the night are going to last more or less the same. They are mild changes in the seasons. But in winter and in summer, you're going to have big changes. Remember that in summer, you always go to the beach. So think of the beach as this place with a lot of sun. So in summer, you have a lot of sun. And in winter, think about Christmas, and you are at night, you are always like near to your fireplace, drinking chocolate, right? So in the winter, you're going to have a big change towards having very few light, and that is going to be a solstice. One is going to be larger than the other. So that is basically the key. Think which station you're going to be talking about. If it is a regular station as spring or autumn, then you're facing an equinox in which you are basically going to have the same length of day and night. Or if you are talking about a very big change, a very strong change in season, for example, in summer, in which you're going to have a lot of heat, a lot of sun, or in winter, in which you're going to have a lot of cold and very few sunlight. Now, let's move towards our next topic, which is layers of Earth, but I'm going to make a small pause here so that you can, write or whatever, so you can pause the video here. Okay, so I hope that you have pause the video and go back to all the parts that you didn't understand, because now we're going to enter another topic of our review, and that is the layers of Earth. So I would expect you to remember from our previous exam and from the previous topics that we were seeing in geography, how we have these basic 3 ways of making models out of objects. We have, first of all, projections, and in a projection you are going to be basically obviously projecting an object into a plane. And that is going to cause this 3-dimensional object to look like a 2nd-dimensional object. The thing that is really interesting with projections is that it depends a lot on the direction and the way in which you are projecting this object. So for example, if you are standing over here, and you project this object towards this wall, it is going to look like this. But if you are looking this cube from above and you project it down to this plane, then it is going to look like this. And these two shapes, these two projections are very, very different. And that is a problem with projections, that you have to take the same picture from several sides so that you can actually know how this object is in reality. And this is something that doctors do a lot. When they take x-rays of you, they basically take this flat picture of your bones and they try to take this picture from several angles so that they can see what is wrong with you, if there is something wrong with you. But this also happens in geography. If you remember, we have seen this when we are talking about the projection of planet Earth, which is a three-dimensional object, a sphere, that we are trying to project into a flat surface and make a map out of it. So we basically can project it in an azimuthal way, we can project it in a conic way, or we can project it in a cylindrical way, as we do when we use the Mercator projection. But again, projections will always have their weak points. Why? Because we are making a three-dimensional object flat, and that is going to depend on the angle that we take, the outcome that we are going to have. As you remember, all projections have their issues and are good for other things. And now sections. When I am doing a section, what I do is that I cut pieces of my object. And I cut pieces because I am usually very interested on what is happening inside my object. So for example, doctors do this too with their PET scans. What they do here is that they take pictures, for example here, of inside your head, because they want to see if there is something wrong in any of the slices that they are able to take. So they will be able to see different cuts, different slices of your head in a picture, and they will try to see if all of these layers are normal or if you have a problem. But over here, we are interested in studying what is inside our planet. So we are also going to do a section. This model is going to be a section. But before we move into that, I'm going to remind you only that we also have surface reconstruction, in which a computer, for example, is going to store the position of a lot of points, and then it is going to join them together. So for example, here, it took the position of a lot of points, and when the computer joined them together, a pig was formed, right? But this also happened when we were studying this geoid made by the European Society for Space and so on. And this is also a surface reconstruction. But these models that you are doing nowadays and that are part of your homework, these are also surface reconstruction. They are based in the position of a lot of points. So we're going to be seeing these models too in very few times. So as you can see, we're seeing all the three ways that we can make a model out of an object. So let's see our section. Now we can basically see that planet Earth has two layers, right? The core, which is divided in inner core and outer core, and the mantle, which has a lot of divisions. First we have the lower mantle, then we have the upper mantle, which is made out of liquid rocks, and then we have the asthenosphere, which is the last layer of the mantle that is still liquid. And finally, we have the lithosphere, that is the last layer of the mantle, but that is now solid. And as a part of the lithosphere, this very thin green layer is the crust. So basically what I need you to see here is, of course, to learn all the layers of the Earth, because they all have special properties that we need to know. But mainly that the inner core is a solid layer of the Earth. It is a solid sphere made out of iron in the center of our planet. And then we have the outer core, which is already liquid. It is also made of minerals, of very pure minerals, but that are in a liquid state. Then we go to the lower mantle, which is made out of also minerals and also some rock and so on, till we get to the upper mantle that is going to be made out of liquid rocks and also the asthenosphere, mixed with a lot of minerals and so on. So it is very important that the asthenosphere is the last liquid layer of Earth, because after that we have the lithosphere and the crust, which is the part of the Earth in which we live, right? So why is that so important? Well, because there are only two layers of Earth that are solid, the inner core and the lithosphere with the crust, of course. So we can think of our planet as a sandwich, right? Only the first and the last layer are solid, and everything in between are liquid layers. And you can remember this really easily if you think about the name lithosphere, because lithos means rock, and sphere actually means sphere. So we are talking about the sphere made out of rock, which is this layer that we have here, a solid layer. And the only other solid layer is the inner core, so only the first and the last one. So this is very, very important because this lithosphere is divided into parts, and those parts are floating over the asthenosphere that is still liquid, so they can move. If the asthenosphere weren't liquid, then these parts of the crust could not move. These parts of the lithosphere could not move around, and that movement is very, very important for us. So now we're going to see this thing called tectonic plates, and what I want you to see here is that we have the plates, which are the lithosphere, these parts of the lithosphere, and they are floating above the asthenosphere. So they are free to move perhaps towards each other, perhaps away from each other, perhaps next to each other, but they are free to do that only because they are floating above the asthenosphere. If the asthenosphere weren't liquid, if it was actually solid, then they could not move around. We would only have this solid sphere of non-moving rock, right? But we don't, because it is divided into pieces, and those pieces are floating above or over the asthenosphere. So the lithosphere, as it says down here, is divided in parts called plates. And those plates are drifting or moving around the asthenosphere that is still liquid. So this is going to get us to a very nice scientific theory that we have in geography and in geology, that are the tectonic plates and continental drift. They are theories that help us explain the formation of mountains, the formation of volcanoes, why and how do we have earthquakes, and a lot of more things. Why? Because well, first of all, this is a theory because it has a lot of background, because it has a lot of proof. It is not like speaking in everyday language when we say, oh, that's just a theory, and we say a crazy thing. No, in science, a theory is something that has a lot of evidence behind it, that is actually proven by a lot of evidence. And what is the evidence that we have that these plates actually exist and that they are moving around in this thing called continental drift? Well, we have the proof of precisely volcanoes, we have the proof of earthquakes, we have the proof of mountains, and we can follow them around like a puzzle, and we can make that puzzle into a nice model that will be telling us which are the parts of the puzzle, where is one part ending and where is another part starting. Of course, this has changed a lot throughout the years, and in continental drift we will be able to see that perhaps there are some mountains in South America that match other mountains in Africa, and that is because these two land masses used to be together. Or perhaps we find a piece of mountain that is in Canada and that also is shared in Russia, and that is because they used to be together, right? So we are going to be following all these traces along with volcanoes, along with earthquakes, and we will be able to see not only that they are moving, but in which position they were found years and a lot of years before us. So there are basically three ways of tectonic movement. There are going to be plates that are moving away from each other, and that is going to be called divergence. And perhaps in this movement, as the plates spread apart, some liquid material from the asthenosphere is going to get out, and that is going to form a volcano over here, right? Or perhaps they are moving towards each other, and that is called convergence. And perhaps from this area here, some of the magma can escape, and that will also form some mountains and volcanoes, right? And that usually happens. Or in transform, as they are moving next to each other, all the friction that is happening here will also form earthquakes, well, mountains, and cause earthquakes. So this is going to have a very, very big influence on the surface of the Earth and on the relief that our planet has, not only above the ocean, but also below the ocean. Below the ocean, these things are also happening because we have continental plates, but we also have oceanic plates, right, that are below the ocean. So this is happening both above the surface of the ocean and below it. Now, this will allow us to explain something really interesting, as I was telling you just a few minutes ago. And that is precisely this ring of fire that we have here. This is the name that it has received. This red line that goes all the way from South America to Central America to North America. It moves to Alaska, all the way to Russia, and goes down to Asia, Japan, East Asia, Australia, and all the way also into the Indian subcontinent, surrounding East Asia, Southeast Asia here, right? So, what is this ring of fire? Well, it is going to be the place of the world where we're going to find the highest amount of volcanic and earthquake activity. And how do we explain that? If you pay attention here, Mexico is actually along the ring of fire, and you cannot deny that we have a lot of volcanoes and that we have a lot of earthquakes, some of the worst earthquakes that there are in the planet, right? So why? Well, because as you can see here, there are a lot of plates interacting along this ring of fire. So we have, for example, the North American plate that over here is colliding with the Cocos plate, which is this smaller plate here. And over here it is colliding with the Pacific plate, that is this massive plate over here. And the Pacific plate is also colliding here with the Nazca plate, and the Nazca plate is colliding with the South American plate. So this is an area in which all the plates are interacting heavily, a lot of interaction, and that is of course going to cause a lot of volcanic and earthquake activity. So this is the ring of fire. That is why it is the ring of fire, because, well, it is filled with volcanoes, it is filled with earthquakes, and the reason for that is that it is the limit, it is the border in between a lot of tectonic plates. So all this activity is going to be causing Earth's relief, which we're just about to study, but I'm going to pause the video here just so that you can return to the video, maybe complete some definitions, write the text that we have in the slides, and keep studying your video, okay? Okay, so now we are back in our third topic, that is Earth's relief. So I hope that you were able to return in your notes and check everything that you didn't have, complete everything, and find everything that you didn't understand in our previous content. So now it is the turn for Earth's relief. Well, first of all, we need to say that not all of the Earth's relief is caused by tectonic movement. There are other elements such as wind or runoff. If you remember, we have seen runoff in the water cycle. So we are going to see this again by the end of the video. I would advise you to stay because it is really interesting. And they will be eroding the surface of the earth. Sorry, in here it is missing. It should say erode the surface of the earth. So in here we have several examples. This rock was clearly eroded by the wind. So wind can be so strong that it can actually defeat rock. And in here we have the example of two canyons, and these canyons were caused by the effect of runoff. So remember that runoff is when water moves in the surface of Earth, and that is going to be moving materials. So through several centuries, all these moving and carrying away material is going to cause canyons, and the rivers are still going to be running in the lower part of them. So all these nice traits of Earth's relief is not caused by tectonic movement. It is caused by other elements of Earth. However, the let's say the traits that we are actually going to study in this moment, because then we're going to see some more of them in the next trimester and so on. We're going to study how, for example, in Oaxaca, when we start cultural geography, we're going to see how in Oaxaca the cultures like Zapotecs knew how to take advantage of these traits of Earth, and they made it part of their social and political life. But for now, the Earth's relief that we are going to be studying is precisely related to the tectonic movement. Not all of the traits of the Earth's relief is related to tectonic movement, but the one that we are about to study is related to tectonic movement, okay? So, well, first, this part is extra. If you want to move along and return, like in a few minutes, play the video forward and return playing it again when you see that this topic is over, you can. But it is very important that you also know how to solve this, because this can give you extra points in your exam, and I am sure that everybody could do well with some extra points. So what is the thing here? Well, the thing here is that we want to model Earth's relief, as we made models of the planet using map projections, and as we made models of the Earth making sections and seeing inside the Earth. Now we want to see the surface. So in order to do that, if you remember, let's go back. In order to do that, we need surface reconstruction. And when you do surface reconstruction, really, is because you care about all the different traits that the surface has. You really don't do a surface reconstruction if you have like a sphere. You don't require a surface reconstruction, you just draw a sphere. You want to make a surface reconstruction when you have rugosity, when you are interested in all these changes in the shape of the object that you are modeling. When you want to pay attention to those details, then you use a surface reconstruction. So we need to make surface reconstructions here, because what we are studying are well, all the traits of the Earth's relief, and that is filled with rugosity. So we're interested in studying that rugosity. The problem is that all this geometry that we have studied so far, even this one about the ellipse and so on, this geometry does not allow us to process rugosity. So we need a different type of geometry. As it says here, Earth's relief is filled with rugosity. In order to model it, we require a different type of geometry with non-integer dimensions. This is the most important part. Why non-integer dimensions? Well, if you remember, this is the geometry that we have been working with. The one that we were using in order to find out distances, to find out scales in maps, to find out scales in globes. This is the geometry that we were using, and it is based on integer dimensions. An integer dimension means that you can only have integer numbers. That means only 1, 2, 3, right? Nothing in between, only integers. But the geometry that we require in order to make these models is called fractal geometry. Why? Because it is based on dimensions that are fractionary. They are non-integer dimensions, as it says here. Non-integer dimensions means that they are not integer numbers, that they have things in between. For example, 0.4, 1.4, 1.8, 2.6. This point something, this is what is allowing me to get into the small little details and actually be able to model rugosity. If I wouldn't have these numbers after the decimal point, then I would only be seeing lines, surfaces, or volumes, but I wouldn't be able to see all the details, all the rugosity. So, this is the main difference. If you remember, Euclides was a Greek guy that built the geometry which we always use at school. You would always see this geometry and only this geometry other than in this class of geography. And it is based on integer dimensions. So again, only the 0, which is the point, the first dimension that are lines, the second dimension that are surfaces, and the third dimension that are volumes. So it is very good to use it, as we have done, if we are studying maps, distances, globes, and so on. The problem is if you have rugosity. If you have rugosity, this model of reality that is offering Euclidean geometry will not be enough for you. It will not be able to process and represent rugosity accurately. So in order to do that, more than 2,000 years after Euclides, more or less 2,400 years after Euclides, Benoit Mandelbrot developed a new type of geometry called fractal geometry. Fractals exist in non-integer dimensions, that is in fractionary dimensions. That is why the name is fractal, because it is in a fraction of a dimension. And they also have self-similar properties. This makes them the best approach or the best way to study, represent, and model problems related to rugosity. So what we want to do now, talking about Earth's relief, cannot be done with this. We require this. So how do these fractals work? You should remember this, but this is going to be a very nice review for you. Well, remember that they are going to be winning or losing dimension depending on the procedure that you apply to them. You are going to be starting in a certain dimension. For example, here we're in the first dimension, right? Just a line. Or over here we're in the second dimension. It is a surface. But you're going to apply the same process over and over again, and that is going to make these objects either win or lose dimension. For example, here in the Koch curve, as I start sectioning this line and adding angles in this, in the two lines in the middle, I am going to start to have these very thick triangles that start to look like stars, right? And that is going to cause this line that I started with over here to win a lot of rugosity. And as you win rugosity, you also win dimension. So in this case, the Koch curve, instead of being in the first dimension, it is actually going to be found in dimension number 1.26. So that 0.26 that we have is dimension that this line is winning through rugosity. As you see, there is no surface here. It is just lines. But these lines are getting a lot of rugosity, and that is winning 0.26 dimensions to our line. Another example would be the Sierpinski triangle. We start here with a surface, right? But we're going to be punching holes, and in this case, those holes are going to have the shape of a triangle. So I'm going to be deleting all these parts of the surface and deleting and deleting and deleting all the way to the infinity if I could have enough time, or if I used a computer to produce these triangles. And as a result, the Sierpinski triangle is actually going to be losing dimension because it is losing all these sections of the triangle. So the Sierpinski triangle lies in dimension 1.58. It has lost 42 or 0.42 dimensions as we cut it out, all these regions over here. All these white parts are taken away, and that is going to make the triangle to lose 0.42 dimensions. So now it is approaching the first dimension. It is not yet there, but it is approaching. So how do we solve it? Well, if you remember, you should know this formula by heart, because this is the formula that you used in order to solve all your exercises about distances, surfaces, and globes. So what is this formula? Remember, it is the number of copies equals the scaling factor raised to the dimension power. So in this case, as the question is the dimension, we're going to need a mathematical function called logarithm. And what is logarithm? Well, logarithm allows me to know to which power do I need to raise one number in order to get another number. So in this case, to which number do I need to raise s in order to get n? That is basically d, right? I want to know d. To which number do I need to raise s in order to make it as big or as small as n? So as in this case, we want to know the power that I need to use to get n out of s. In other words, we are looking for the d of the formula. It says over here. So how do I solve it? Well, this is the way to write the logarithm like in a usual way, the mathematical notation. Logarithm of base s because this is the number that I want to raise to get another number, and n is that other number that I want to get. So logarithm base s of n. And how do I solve it? Well, it depends. If you're in your iPhone, remember you write n log 10 equal, then division s log 10 equal, and that is going to give you the result. But if you're in Android, you can write it in a cleaner way, log n, just remember to close the parentheses, division log s and close the parentheses, hit equal, and you should have your dimension. Just do not forget to close the parentheses in Android and to write first the number and then the log and hit the equal sign when you are finished in iPhone. And that is going to be able to give us d. The question is, in order to get d, I already need to know s and n, right? So how do I get s and n? Well, n is always going to be the amount of pieces of the same size that I can count in the whole figure. So if we look at this figure, the parts that are still existing, because all the blue parts do not exist, the parts that I still have of my Sierpinski triangle are the black parts, and those are 9 parts. 1, 2, 3. Let me count it for you, because remember, there are always faster ways to do this. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Or I could just count that over here I have 3 and that I have other 3 triangles of the same size, so that is basically 9 again, okay? So my total amount of triangles is 9, and that is going to give me my n. So now everything that I have to do is count my s. And how do I know my s? My s is the amount of pieces of the same size that I can count in only one side, not the whole figure, only one of the sides. So again, I can count only here, and I'm going to have 1, 2, 3, and 4. Those are the only pieces that I have in one side. So that means that my s equals 4. N equals 9 and s equals 4. So I am going to use this logarithm, log base 4 of 9, or in iPhone I would do this, and in Android I would do this, and basically I'm going to get 1.58, which we already knew. Now, let's make some exercises that you already have in your notebooks, but perhaps you would, well, it would be better if we see them again. Let's start with the Sierpinski's carpet. I am going to solve this part over here. Let me use another color, perhaps another tool. I am going to solve this iteration here, this one. So the first thing that I want to do is count all the pieces of the same size that I have. So what do? I count 1, 2, 3, 4, 5, 6, 7, and 8. So there are 8 pieces of the same size in just this small section, right? 1, 2, 3, 4, 5, 6, 7, 8. So how many sections like this one do I have? Well, I have 1, 2, 3, 4, 5, 6, 7, and 8. So basically the total amount of squares of the smallest size that I have is 8, because I have 8 in one of these ones, times 8 because I have 8 of those sections. So that equals 64. And how many do I have in only one side? Well, let's count them. For that I will have to erase this gibberish. So now we have 1, 2, 3, 1, 2, 3, 1, 2, 3. So basically in just one side we have 9, right? So what we want to find is, well, the power that will make 9 as big as 64. So let me write it again, but in a nicer way. I have that the total amount of squares of the little size is 64. I have that in only one side I have 9, so now I am going to do log of base 9. That can give me 64, which is the same as saying, let me erase it and write it again in another format. It is the same as saying log 64 between log 9. And let me do that in my cell phone. Give me a second. You can be doing it now too, so that you don't lose any time, but basically 64 log between 9 log, and it equals 1.89. The dimension of this object, the Sierpinski's carpet, is 1.89. And the same would happen if instead of counting, well, all those small squares, I would just count, let's say, these squares here. And if I count the total amount of these squares that I have, I am going to have 8. So n equals 8. And if I only count one side, s equals 3. So if I write log of 8 between log of 3, I am going to be getting exactly the same. So it doesn't matter. Perhaps in the exam I will ask you to solve this iteration, perhaps I will ask you to solve this iteration, or perhaps this last iteration. But they are all solved the same way. Just count the total amount of squares that you have of the same size, and then count how many of them do you have in only one side. And that is it. Now let's work in another example. We can do the Koch curve. So in the Koch curve, what I'm going to count is how many pieces do I have. So I start counting 1, then I start counting, sorry, well, let's use that one. 2, then 3, and finally 4, right? So my n equals 4. The lines that I have in the same size, okay? So now I want to measure just one side, but using this size. This is going to be my ruler, and I am going to measure this side. So how many times do I need to use my ruler to cover the whole length? Well, 1, 2, and 3. If I use one line as a ruler and I only count one side, then it has 3. So my S equals 3. 3 times the same ruler. So what I need to do is log 4 between log 3. Let me do it. 4 log between 3 log. And, sorry, I made a mistake. Log 4. This equals 1.26. Sorry for that delay. It took me longer than expected. So 1.26. So as you can see, it is winning dimension. Instead of losing dimension, as it is winning rugosity, it is starting to win dimension. So if we would solve it in the next iteration, and remember that the answer was 1.26, I'm going to write it again down here so that we don't forget. The answer is 1.26. So let's count the next iteration. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. N equals 16. Always be really careful because there are a lot of mistakes that you can make if you do not count properly. So now I'm going to use this as a ruler. If I want to measure this whole side using this as a ruler, how many rulers do I need? Well, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So S equals 9. So log 16 between log 9. Let's do it. 16 log between 9 log. And again, we get 1.26. So it is correct. It doesn't matter if in the exam I ask you to solve this iteration or this iteration or this one or even this one, the process and the result is going to be exactly the same. One more exercise. Let's continue. We have 2 more to go. Let's move forward, to the Cantor set. This is actually one that I enjoy a lot because it seems to be really easy, but it is not. Well, what do? I count the amount of pieces that, let me just go down here. Yes, I am going to count the amount of pieces that still exist. So I am deleting this part over here. This doesn't exist anymore, right? So I'm going to count. I have 1 piece, 2 pieces. The amount of lines of the same length, remember, they always have to be of the same line. The total amount of lines of the same length is 2. And if I use one of these lines as a ruler, how many do I need in order to cover the whole side that is here? Well, that is 3. So that would be log 2 between log 3. And in this case, pay attention. The smallest amount is the first logarithm, and in other cases, it is the other way around, right? But now we're getting as a result 0.63. So it is losing dimension. It started off as a line that is in the first dimension, but now it lost a lot of dimension and we find it in the points in the 0.63. So what would happen if I would count another iteration just to make the experiment? And again, I am going to write our result over here just so that we don't forget 0.63, and we can see if we get the same. Let's count here. I have 1, 2, 3, 4. I have 4 lines that actually exist, right? And if I use this as a reference, how many of them do I need to fill the whole line? So I have 1, 2, 3, 4, 5, 6, 7, 8, and 9. I need 9 lines. So my scaling factor is 9. So what I would do is logarithm of 4 between logarithm of 9. If I do it, 9 logarithm between 4 logarithm equals 1. Oops, I made a mistake, sorry. 4 logarithm between 9 logarithm, and it is 0.63. So we are absolutely right, okay? Sorry, so the final one. Finally, this one is really easy, right? I don't know actually the name, but I would call it some Koch variation, perhaps. I don't know, Koch variation. So a change in Koch. Instead of doing this, now we are doing this, right? So how do I measure it? Well, I am going to count. As you see, the iterations get really complex with this one. This is just the second step, right? And it is already that complex. But let's solve only this very simple one that we have above. So we have one line, two lines, three lines, four lines of the same size, 5 lines, 6 lines, 7 lines, 8 lines, right? 1, 2, 3, 4, 5, 6, 7, 8. My total amount of lines is 8. And if I use one of them as a ruler to measure the whole side, I have 1, 2, 3, and 4. 1, 2, 3, and 4 lines of this same size. I require 4 of them, so my scaling factor is 4. So that is log 8 between log 4, which gives me 1.5. So it is right in between. But this one is really important. Why? Well, if you make this same process, but you take it into a surface and you say, okay, I'm going to make some of the squares or the cubes go up and some of them are going to go down. And you repeat that process, like this one is going up, and in here 2 are going up and 1 is going down. And you repeat this process, right, several times, just at random. Let the computer choose. Well, you're going to have something like this, perhaps. You can use this procedure to build Minecraft landscapes, and it is going to work really well. That is actually how Minecraft works and how it is produced, all the landscapes. But what happens if instead of making these squares in order to get my surface, I use these sort of triangles over here? Then I can make really, really nice landscapes, right? And perhaps I'm going to tell my computer, well, everything that is below certain height, make it blue because it is the ocean. And as it starts to go up, make it green because it is getting out of the ocean. Now it is the mountain. And then make it brown because over here it is too high, so plants cannot grow. And just in the peak of the highest triangles, make them white because that is the snow. And I am going to be able to produce very nice landscapes like that, right? And these are fractal landscapes. Why? Because this is not a three-dimensional object. This is just a surface which points we are moving around, up and down, up and down. It is a surface, but we are moving some of its elements up and down. So it is in a fractionary dimension. And once we have this, now we can make models. And if we have models, now we can study what we want to study. So this is the model that I made for you when I was working with the simulation that I asked you to use. And this should be very similar to the homework that you have to deliver me, right? Except for the definitions. You should also have the definitions in here. So what is a continental slope? What is the oceanic crust? And so on. And that is precisely what we are going to see now. I am going to use these two images, and then I am going to use another one that I found that I think that will allow you to understand a lot better. Let's start with this one. First, we have a division. There are some parts of the lithosphere that are the continental crust. So those are the parts of the lithosphere that rise above the sea level and make up the continents. And we have the oceanic crust, that is the part of the lithosphere that lies below the ocean. Sorry, that lies beneath the ocean, that lies in the bottom of the ocean. Of course, as the continental crust is going to start to go up, and it is going to start to get out of the ocean, it is going to be higher than the level of the ocean, we're going to have this thing called the continental slope. And it is precisely this inclination that is going to be making up let's say, the rise of this plate into dry land. So that is the continental slope. And of course, once we get to this division between the ocean and the dry land, that is the coast, right? It is the division between the ocean and the land. But there is a part of the continental shelf that is still below the ocean. Like, this is the part where you swim when you go to the sea. You don't go to the oceanic abyss, and you don't like go several meters below the sea level, right? You only stay in these very nice beaches that we have, or in other countries, but you only stay in the continental shelf. What is the continental shelf? Well, it is the very small part of the continental plates that is still below the level of the ocean. So it still is covered by the ocean, but it is starting to get to dry land, and we're going to start to have the coast and mountains over there. But just before we get to that point, the continental shelf is going to be that last part of the continental crust that is still underwater. So you can see that it is barely underwater. These are our beaches, right? The places where we swim. Now, I want to change my image because I want to explain you what is the continental rise. As you see here, this is the continental slope, right? And we could draw actually a line here, and we could say this is actually the continental slope, this one over here. So what is the continental rise? Well, as you see, this is the ocean, right? All this part over here is the ocean. So the ocean is moving towards the coast. This is the coast. And it is moving materials, perhaps some rocks, perhaps some sand, some shells, I don't know. But of course, it is not able to push them all the way up into the coast. So they are going to remain here. This is all the material that is being accumulated in this low part of the continental slope because the ocean cannot carry it up into the coast. So that accumulation of material that we have in the lowest part of the continental slope, that is the continental rise. It is a bunch of sediments and materials that the ocean has moved towards the coast, but that it cannot go up because it is facing the continental slope, okay? So finally, of course, we know that the ocean is this large body of salty water, and we basically have all the elements that we require in our model. So please be sure to check your definitions, to have them, to be able to understand which one is which. So again, the continental slope is, the part in which the continental plate is going to start to go up and go out of the ocean. But the small part that is still below the water, that is the continental shelf. The continental rise are going to be all these materials that are going to be accumulated in the bottom part of the continental slope. The oceanic crust is the part of the lithosphere that lies below the ocean. The continental crust is a part of the lithosphere that rises above the sea level and makes up the continents. And I think that is all, right? The coast is the division between the ocean and the dry land. So again, remember, these plates can move because they are floating above the asthenosphere. So now I only want to show you precisely this. This one, I don't know if it is in French or if it is, I don't know, in Portuguese, I really don't know. But I want you to pay attention to this detail here, the lithosphere. This is what I need you to understand. All this that we are modeling, all this rugosity that we are trying to process here is in order to study one of the layers of the Earth. Which layer of the Earth? The lithosphere. So what we have done all around this using mathematics and different models is trying to make a model of the last layer of Earth, of the lithosphere that we have over here. Yes, boys and girls? So again, I am going to pause this video and you can go back and study everything, your definitions, your logarithms, everything that you require in order to get this part right. All the logarithms and fractals and so are extra points in your exam, but this part of the traits of Earth's relief is obligatory and you need to know it and solve it, okay, girls and boys? Okay, so finally, our last topic, and I do expect you to study this video in more than one day because it is quite long, right? We already have an hour of content here. But you have everything that you need to know in order to solve your exam. So if you really study, not only watch, but if you really study this video, you will be able to have a 10 and even an 11 or a 12. I am really sure of it. Just be sure to understand all the topics in this video. So the water cycle, I know that you may think that this is going to be the easiest part, but I can promise you that we have a surprise by the end of this video. So it is really easy, right? When we are in the sea level and we reach 100 degrees due to the sun, to the sunlight and the sun rays, then the water is going to change its state of aggregation. It is going to become vapor, water vapor, and it is going to evaporate. So when water becomes vapor and it goes up, it is called evaporation. Then it is going to become water again, small little drops in the clouds, and that is called condensation. When that water falls in the way either of liquid, of rain, or of snow, that is called precipitation. Then how all that water goes down from the mountains and out of the lakes, that is called runoff. Remember that the runoff is the movement of water above the surface of the earth, and that is it is also going to be causing some effects on Earth's surface that we are going to model by the end of this video really fast. And finally, when we reach a part of the surface in which water gets stored for a period of time, that is called storage. So basically we have evaporation, we have condensation, we have precipitation, and we have runoff. And runoff with all the effects that is going to have on Earth's surface, which we are about to model. And storage, in which water, well, gets in one place for a period of time, right? When a large amount of water gets stored. So this was really easy, right? So let's see what we can do with this, if we can do something more interesting. Well, what if in order to model everything that the runoff, remember the runoff is causing on Earth's relief, because let me try to go back to the right slide, and we're going to see here precisely, this is the effect of runoff. This is the effect of runoff. So we want to find a way to model those effects over Earth's surface. So over here, I think, let me move a bit. Okay, so what if we use fractals like this one? This fractal was actually developed by Benoit Mandelbrot, the guy who originally thought about fractals. And fractals were developed in order to solve a question of geography, actually, and that is the coastline paradox. How can I know the length of a coast if it is filled with so much rugosity? So Mandelbrot, in order to solve that question, developed fractal theory. And this is the fractal that he himself invented, that he developed. It is based on these shapes like of hearts that get repeated all over and all over again. It is a really complex fractal. But what if instead of using these shapes like hearts, we start to use something like branches? We have a line, and then we add other lines and other lines to those lines, and we repeat the same procedure. Well, these branches are actually how trees are made. And we're going to learn about that the next trimester, how there are fractal properties in living things, such as plants and so on, and also animals like us, because if you look here, this also works as our veins, right? As the veins of our body, and our arteries and so on, our circulatory system in general. So we have these types of fractals in living things. But what if we take this branching, let's say, to a higher degree? Well, we can make very nice trees, yes. But if we modify a bit this procedure, then we can get fractals like this one, really interesting fractals. We can observe this kind of pattern, of branching pattern in nature a lot. This is a type of broccoli. This is Roman broccoli. You can actually eat this. This exists in reality. It is not computer made. And you can see this branching procedure also in trees, and then the branch of a tree, and then the leaf of a tree, and then the smaller regions of the leaf of a tree. And you basically have the same pattern of branching. But if I go a bit deeper and I start to use this type of branching in which I am also changing some of the heights, for example, here you can see that the red areas are high areas and the blue areas are deep areas, then I am able to actually model the effects of runoff over the surface of the earth, and I can get something like this. And this, let me tell you, this is not a fractal. This is a picture from Google Earth, as you can very easily see. But you can really get your mind on the idea that, well, there are a lot of things that we can model in nature, but only if we use fractals, because fractals are able to process rugosity. And if reality has something, that is rugosity. So this would be the summary of our second half of the trimester. Boys and girls, study, study, study.